When we have a variable such as temperature that is a function of position x, y, and z and also of time, what we want to be able to do is to take the derivative of that temperature and be able to express it in terms of the local time rate of change of the temperature and the advection component, bringing in colder or warmer air from another location. If we do a Taylor series expansion, doing del t, we'll get partial t over partial x times del x plus partial t over partial y times del y, etc., plus higher order terms from the Taylor series expansion. If we ignore the higher order terms and we divide everything by del t and take the limit as del t approaches 0, we'll get this following expression where the total derivative is equal to partial t over partial t, temperature and time, plus partial t over partial x times dx over dt, partial t over partial y, dy by dt, and partial t over partial z, dz by dt. But we know that dx by dt, dy by dt, and dz by dt are components of the velocity vector u, v, and w. So we can rewrite the total derivative of the temperature in terms of the partial derivative with respect to time, and then the u, v, and w components of the velocity vector times the temperature gradient in the x, y, and z direction. Or we can write that in shorthand notation, partial t over partial time plus v, which is your velocity vector, dot product with the gradient of temperature. And we can rearrange this and solving for the local time rate of change. Partial t over partial time is equal to the total derivative minus the v dot del t. So physically, what does this mean? The partial derivative with respect to time is what we call the local time rate of change. So at a fixed position, so at this fixed position over here, we want to know how is the temperature changing with time at that location. And the two things that are driving the temperature change at that location are the change following the air parcel. As an air parcel is moving towards this location, what is happening to it? Is it warming up due to the absorption of solar radiation? Is it cooling down due to the loss of infrared? Is it being warmed up by latent heat release? There are a lot of things that can do that diabatic heating that can alter the temperature of that air parcel as it's moving towards our fixed location. Of course, the other term here, the minus v dot del t, now represents a temperature advection term. So up here we have isobars of constant pressure, and then we have isotherms of constant temperature in terms of the dashed lines. So we have a colder temperature, warmer temperature, warmer temperature. And you'll see that the geostrophic wind here that's parallel to the isobars is blowing at an angle across the isotherms. And this is going to be bringing colder air to our site. And we refer to that as temperature advection. When we bring in colder air, we refer to that as cold advection, and that would be a minus v dot del t less than 0. If the opposite were the case and we were bringing in warm air to a given location, that would be referred to as warm advection, and minus v dot del t would be greater than 0. So let's take a look at two hypothetical situations. So the first is following this air parcel. Following the air parcel, the temperature in a Lagrangian sense is less than, the dt by dt is less than 0, and that's due to radiational cooling. Let's say it happened to be at night. At this location, the minus v dot del t is less than 0 due to the cold advection. So both of those processes are causing a temperature decrease at that site to be observed. So the local time rate of change, partial t over with respect to time, is less than 0, and that site will be cooling. We refer to the local time rate of change as the Eulerian reference frame, and the reference frame following the air parcel itself is what we call the Lagrangian. So in that case, both of the temperature advection and the Lagrangian temperature change following the air parcel were both cooling, which caused a local time rate of change for temperature, which was cooling. Let's do a different hypothetical. In this case, let's say that the total derivative of the temperature is greater than 0 due to the absorption of solar radiation during the daytime and conduction in contact with the ground. And for this location, there's still cold advection going on. So the local time rate of change at this location could be either positive or negative, or could be 0, depending upon the relative magnitude of the heating that the air parcel is experiencing as it's being advected toward the reference site, and the strength of the cold advection. So this would be an example. It's possible to, after a cold front passes and you've got that cold advection coming in, and then you have strong sunlight the next day where the temperature really just doesn't change even though you have bright sunlight. And it's because you have a balance of these two changes. One is the heating up of the surface during the day from that sunlight. The other is the cold advection, and they're balancing each other out. That's one hypothetical. But the total derivative is the mechanism by which we can actually do this for any of these multidimensional variables. So we can do this with regards to pressure, we can do this with regards to momentum, et cetera, et cetera. And so we can look at the local time rate of change of the dew point temperature if we wanted to look at the advection of moisture and the addition or removal of moisture due to evaporation or condensation. It's a very powerful tool for being able to diagnose how the local time rate of change of an air parcel is going to be impacted by a combination of processes that are happening with the flow and processes that are happening in terms of advection.